Welcome to Unlocking the Language Model Magic, LLMs Demystified with Eric and Kevin Wu. Eric and Kevin are instructors of CoRise's Deep Learning Essentials course starting next week. And I will pass it over to them to begin.
Hi. Yeah, thank you, Barbara. So just to introduce ourselves a little bit. So Kevin and I have been working with CoRise for the last a little over a year. We teach the Deep Learning Essentials class, and it's been a lot of fun so far. We will be running our fourth run of the class in a week. So starting June 19th, where we really cover the basics of deep learning. It's for everyone who's interested in learning about deep learning, machine learning models. So we really start from the basics. All you need is a little bit of coding experience. You don't need machine learning background. And our goal with that class is really to give you all the essentials that you need to start using deep learning, either in your work or just on the side if you have interest. Yeah, before I turn it over to Kevin, today we just wanted to talk about large language models, which is the latest class of very powerful neural networks. There's a lot that's been covered in it. I'm sure all of you are familiar to some degree. And we feel that as much press as it gets, really under the hood can be quite opaque at times in terms of how they work. How would you go about using it? With tools like ChatGPT, all of that is hidden. So you get a really nice user interface. So we really just wanted to lift that hood today and spend a little bit of time going into first how LLMs work at a basic level under the hood. We wanted to talk through ways in which you can leverage LLMs through fine tuning or other means to adapt to your specific needs. And finally, we want to talk a little bit about potential risks and biases of these very powerful tools and how to be aware of them.
Okay, great. Yeah, so excited to talk on this. Again, the goal today is just to provide an overview, and there's always more details to be involved. So feel free to ask questions, and also we'll get more in depth in terms of LLMs for the course to come. All right, so let's just get started. So LLMs are the new hot topic of 2023. As see here, we have this interest over time, and specifically within this 1 year, we have a fourfold or so increase in LLMs. The thing is, LLMs have been used starting 2016. This is something that has come out ever since the folks at Google had really focused on what self-attention is when the advent of transformers, and they started training a lot of data. The question now is, why are LLMs suddenly a large topic? And a lot of it has to do with just how broadly it's being used and how relevant it is to everyone's everyday lives now. So the reason for this talk is that many people are using LLMs through things like ChatGPT or things like Stable Diffusion, but few people can understand them. And then even fewer people can fine tune them, actually do something with the model such that they have some control over what the outputs might be. And so this is something that we feel that if someone in industry or in academia were to have a more in-depth understanding of this, it really does help with being able to be claiming themselves as an AI expert and also be able to get the most out of what these models are capable of. Okay, so this talk, we're going to go over three basic things. First, we're going to give a quick explanation of what LLMs are. Second, we're going to give an overview of fine-tuning LLMs. And finally, we have just a few things to consider that has to do with things like biases and also different trends that are occurring right now within this industry. Okay, so the large language model, as you see on the right-hand side here, this is only even recent as of December 2022, but the circles here represent the number of parameters in each model that are being trained, and every circle is an LLM. You can see there's just really an explosion of the number of these models out here. Most people are familiar with GPT-3, it's on the left-hand side. Really what people are using is GPT 3.5 when it comes to most of ChatGPT, and then there's a GPT-4, which is not in here because people just don't know how many parameters are being used in that model either. Okay, let's focus on what makes a large language model large, right? That's basically the biggest differentiator of this term, a large component of this. So it's large in two ways, right? First, it's the model parameters, as we've seen in the previous slide, and now this is more of a direct bar chart. Just the number of parameters being used is very large. And just to give you an order of magnitude comparison here, so here we have number of parameters like 10 to the 10th or 10 to the 11th. At the advent of deep learning, the first neural networks to really break state of the art had something like 50,000, maybe 100,000 parameters. And those are considered really large models because before neural networks, you had more simple models like logistic regression or random forest, and those would at most come with 10,000, maybe 1,000 parameters the most. So yeah, this is the first axes here. We have different tiers on the x-axis, the y-axis here. Things like Elmo or BERT are some of the predecessors for GPT. And then GPT itself is particularly focused on the generating component. And that has many different versions, as you might see in code later, small, medium, large, extra large. And so this is how the different sizes and also proportionally the performance of these models are also that. Okay, so the second thing that makes a large language model large is the data set that's trained. And so there's a bit of this parallel to with a large model, you also have a large data set. And the question is, which one came first, the chicken or the egg? Are these models large because they have a lot of parameters and so you need a lot of data to train them, or because the data sets are large and you need a lot of parameters? In this case, it's because there's a lot of data. And so you need a lot of parameters to be able to learn that data in an effective way. And so if you look at a lot of these corpus sizes, basically they are also very large. On the x-axis, tokens basically refer to, you can think of them as words, but maybe sometimes smaller bits of words, but essentially something like number of words. And you already are in the scale of billions of words, tens of billions, hundreds of billions of words. And so this is an incomprehensibly large data set that needs an incomprehensibly large model to learn it. So here's a couple of schematics in terms of where the size of data sets come from. So if we look at the first chart here, this is the OpenAI GPT models. So over here, we look at what is the composition of the data set used to train these large language models. For the most part, it's the internet. As we know, Common Crawl is we believe through a nonprofit, they basically gather a lot of data from the internet. It could be from different places like news publications, places like Reddit, we could be taking things off of blogs, for example, and they do a filtering on it for quality of content. And that by and large is the 60% weight in the training mix. So 60% of the data comes from just parts of the internet. But then you still have significant components of it coming from things like books and Wikipedia. But to me, the largest scale component here is just the fact that we have Wikipedia, and that to me is already incomprehensibly large, and that's only 3% of the data set. Okay. Finally, we just have the different makeup on the bottom part here. This is an alternative view just in terms of what makes up Common Crawl, Wikipedia, and books, and so forth. So this just gives you a little bit of flavor. Okay, main thing about LLMs is that they are not trained for any specific purpose yet. In other words, by purpose, I mean that we have a lot of things we want things like ChatGPT to do, translate my text or summarize it. It's not trained particularly for those yet. It's simply just trained to learn language. And so for the next few slides, we're just going to go over pretty quickly how that happens. Just train for a general purpose language understanding. And that's the core of what it means to pre-train a language model, which leads into fine-tuning later. Okay, so these next few slides, I'm going to move through a little faster because really to get to know this is to also code it up a little bit. So hopefully this gives a little flavor of what the class might look like. But if you have any questions, we're going to have a Q&A at the end as well. Just feel free to ping that up. Okay, so there's two basic self-supervised objectives. An objective is essentially saying we have some kind of a target that we're trying to get better and better at doing. And there's two things. So masked language modeling and next sentence prediction. So let's go through an example of what this looks like. So these models learn language by predicting masked words within the other words in the text. For example, if I have a sentence, the book was so captivating that I read it in blank night. Most of us, with our understanding of language, can fill it in with some words that might be reasonable. That I read it in one night, that I read it in the whole night, or something like that, right? We could just fill in something that based on the context, we know what might be missing. Something like, I need to buy some blank for the recipe I'm making tonight. I need to remember to buy some blank for the office party tomorrow. It could be any number of things for the office party tomorrow. But that by itself gives a task for the model to be able to do. And it's really predicting what this word might be. The model here is being fed a sentence. Here, for example, the dog ate treats for dinner. We might mask out the word treat And then after that, we are asking the model to predict, okay, what was that word? So it could have been chicken, it could have been beef, it could have been kibbles. And then we just repeat that again for different words that are missing. And then at the end, we try to fill out what that word might be. So that's the essence of what we have before, which is called mask language modeling. That's the first part. So very simple. It just takes words out and it asks the model to predict what that word might be. Okay, the next thing is called next sentence prediction. So if we think about it, instead of at a word level, we have it at a sentence level. Imagine here's two texts, and you don't have to read through the whole thing, but one is about coffee, the other is about Australian Shepherd dogs. And then you're to just take a sentence or a pair of sentences out from each of those texts, or the first sentence, second sentence, and the last two sentences in the second text. And you were to put them next to each other. So the model takes two sentences and outputs, did one sentence follow the other sentence? The dark blue follow the light blue sentence in order. And if so, yes. And then you also give it examples where it doesn't follow. And if so, no. So this is a binary outcome. It's either yes or no. And the model gets trained to be really good at differentiating where the sentences should be. And the idea here is that there's more context here, and we need to understand what the whole paragraphs are about. If you're talking about coffee and you're suddenly introducing Australian Shepherds, it probably isn't from the same paragraph. And overall, we get this idea that you're coming into this with two levels of abstraction. First is mass language modeling, and that's bottom up. You get a really good fine-grained understanding how sentences work. And that later on, when we're generating words and sentences with ChatGPT, this is a lot of where that capability comes from. But also, you learn how whole paragraphs work, and entire semantic meaning of entire essays might work. It's next sentence prediction. And that just says that you know that you're on topic, you know that you're producing relevant material at a high level. Great. And before we get into fine-tuning LLMs, the key idea is how are LLMs trained? Because fine-tuning essentially is saying that we're doing additional training at a smaller scale. They're just trained on large corpuses over large periods of time. So GPT-3, which is one of the earlier predecessors for ChatGPT, used around 1,000 GPUs, and these are A100 GPUs, and mind you, these are state-of-the-art GPUs, and it took around a month to train. So imagine you just had a whole giant warehouse that just had 1,000 GPUs just running around the clock for 30 days. And that's how long it took to train on this mix of data that we see here. And a lot of times is actually, we don't know how long it takes to train some of these models. For example, GPT-2, when they wrote the paper, they said the models are still not at the full capacity yet. And as of the moment of writing the paper, it's still training. And so this is one of those themes where it just takes a long time. And nobody really knows exactly at what point you're going to get the best loss. We can try to come up with scaling laws, and we can come up with kind of predictions and so forth. But this is, if we were to add a third large component of LLMs, it's just the large amount of GPUs and costs it takes to train these things. So hopefully that motivates a little bit about why fine-tuning is more desirable, because you really don't want to train your own LLMs. So that's not something we're going to cover in our deep learning course. We're not going to make you pay for 1,000 GPUs, but maybe for the average Joe, me and you, we're capable of fine-tuning. Okay, so I'm going to hand it over to Eric for the next part.
Great. And just to reiterate, if anyone has any questions, you also don't have to wait till the end. You could post it in the Q&A, and then while I'm talking, Kevin can also answer some questions asynchronously, or we can just answer them at the end. Great. So when we talk about fine-tuning, there's really several strategies that are involved in this, and we'll go through each of these, and they have a continuum. First, we can update all the weights of the model. Models have billions and billions of weights. And so the first sort of most strict sense of fine-tuning is where we allow all the weights to be updated, and we train end to end. This can be difficult. So there's other strategies, such as just freezing most of the weights and just training the very end of the model. And this is shown to have almost just as good performance at a much lower cost. And there's other strategies, like you can use the LLM to generate embeddings and then train a smaller model on top of that. And finally, you can just look at things like that don't involve training weights at all, like in-context learning or prompting. Kevin, if you want to go next slide. So here we just laid out in terms of a timeline, right, from easiest to hardest. And this is to give you a consideration of what are the trade-offs involved. So here I have some nice graphics to show when you're thinking about fine-tuning, it's usually in the context of I have an LLM or I want to use an LLM, and then I want to adapt it to a domain that is more specific than what the LLM has been originally trained for. So an example of this, let's say healthcare. I want to deploy LLM in terms of figuring out some things like maybe automatically processing some patient records so I can extract information from there. And so as we're thinking through these things, there is a sort of trade-off. So here we talk about, number one, a feature-based approach. This is, corresponds to us using the LLM to generate some embedding. And so embedding we could think of as like a machine language, not interpretable really by us, but it's just a vector of weights in which we can then use that and then as input to a much smaller classifier and then teach that classifier to use those embeddings and then perform some tasks. Then as we move to the right, we can actually say, we don't have to update all of the weights. Maybe most of them are fine as is. We'll just train the very end of the model. And as we know how neural networks work, there's a sort of bottleneck approach. So at the end of the model, we end up having more higher level semantic learned representation. So it's useful to just use those very last ones. And so we're really just training a fraction of the weights. And empirically, this shows that actually gets us most of the way there a lot of the time in terms of performance. And then all the way at the end, we can say, maybe that's not good enough. Maybe I have the compute resources. I can train all the models. But this is just to give a sense of there is some trade-off as you're considering this. Next slide. So here, just give some heuristic pros and cons for each. Starting on the left, full fine-tuning is the most prohibitively expensive. Really, we give a lower bound of $100,000, where this is what people have reported. You may get the best results here, but in terms of your setup, it does require multiple GPUs. And really, there's a lot of overhead in terms of thinking about almost like systems engineering. So how do I deploy a distributed program? So I want to distribute across many GPUs because a single model can't fit on just one GPU. So this really requires a lot more overhead. But as we move to the right, we see, again, maybe last layer fine-tuning. It still requires significant compute, maybe hundreds of dollars or more, but it's much faster to train. And again, may get you most of the way there. One thing we'll do in our deep learning class is actually do this third option, which is train on the embeddings. So large language models generate, again, this kind of machine language rather, and then we can train like a neural network classifier on top of that for some tasks that we care about. And this can fit on a single GPU. So think if you use Google Colab. And then there's been a lot of talk about prompt engineering. This requires no technical prowess. You don't have to learn a code, but it's really just encoding what you want and specifying that in the prompt itself. And there's cons here. It can be finicky to figure out what are the best prompts, but it's really the most accessible here. Okay, next slide. So we're just going to give a few pointers for each of these. So if you're thinking about actually fine-tuning these weights, whether it's training the whole transformer model or just freezing most of the transformer and training the last few layers, there's a few considerations here. So OpenAI, so that's the company behind ChatGPT and GPT-3 or 4, they have great APIs here. And so first of all, they offer a fine-tuning API. And so what's involved here is you give it an input file, like a JSON file that contains pairs of a prompt, and then your reference generated text, what you want the ideal response to this prompt to be. So you can just give it a lot of these pairs of data, and then you feed it into the API, and they'll actually train and save a fine-tuned model on the back end for you. There might be some considerations here in terms of how slow that might be or the costs. There might be some bottlenecks in terms of just the API being available. So I would consider these. There's other open source tools as well that Hugging Face offers. So Hugging Face you can think of it as almost like a GitHub for machine learning models. There's a lot of open source resources there. So some of these are like AutoTrain, which does a lot of this backend work for you. It specifies what model you want and how much resources to devote to this. And you can upload like a CSV file with your training data there, and it'll run a lot of this automatically. There's a transformers module as well. That's a little more lower level. So you'll be using PyTorch, but it's a high level API in the sense that you can just specify which models, again, you want to use, which GPUs you want to use. So if you're familiar with using Python, PyTorch, this might be a good tool as well. And then finally, at the lowest level, if you say, hey, I want to get my hands dirty, roll up my sleeves, there's still a lot of good open source models out there. For example, Llama by Meta, right? Alpaca is a fine-tuned model on Llama by Stanford. So these are all models in which you can download yourself, your local environment, If you have the GPUs for, you can load it and then do fine tuning. And both of these, they have GitHub resources where they'll actually show you exactly what commands to run. So this is just to give a small lay of the land in terms of if you wanted to do your own fine tuning, here's a couple of options for you here. Okay. So I'll pause here. I'll see if we can answer one or two questions. So Andrew asked, can you comment on which models APIs make the actual model available for fine tuning? I think some models only provide an inference API. Some have API for fine tuning. So I'm assuming that this refers maybe to like OpenAI's API for fine tuning. It's a good question. So I think it's up to which ones they offer. It's unclear if they have their latest model available. My impression is that it's available for their 3.5. And so maybe they've opened that up as an option that you can specify. In terms of these other open source models, you do have to have a sort of request permissions. And so there's usually some sort of a licensing involved. I've seen where if you're using for research purposes, it's free, but if it's commercial, there's some licensing involved there. So I'll look into that. And then one more, what happens if we choose to fine tune an already fine-tuned model? Yeah, that's okay. You can do that as well. So yeah, again, like typically people will take a model which is just pre-trained. So you think about what Kevin talked about, like masked or sentence prediction. It's not trained for question answer per se, and then fine-tune it for that purpose. But you can also fine-tune one that's already been fine-tuned for that purpose. And then accuracy of LM, we can get to that later. That's a really interesting question. Again, a bit of a chicken and egg in terms of like, how do we define our goalposts here? Okay. Yeah, that was on one end in terms of if you actually wanted to update the weights. There's this other end, which is the field of prompt engineering, which to many can feel more like an art than a science. Currently, there's just a lot of effort put in here because precisely you don't need to update the weights. Anytime you need to touch the weights of a model, you have to get into some really finicky business, like how do you even load all the weights of the model into your GPU? It is very expensive. An alternative here is that because large language models can take in a prompt, and these prompts are, the maximum size is getting larger and larger, you can actually encode some training data into your prompt itself. So this is the field called in-context learning. So for example, if I'm asking ChatGPT to solve some math problems, I can provide examples of questions and answers in my prompt and then ask it to solve a new question. And this shows empirically can improve the performance of the model significantly. A subset of this called chain of thought prompting. So this is breaking down your problem into multiple intermediate tasks. So if you describe, if you want to solve this math problem, here do step 1, step 2, step 3, and you arrive at the answer. This is a way of coaxing or teaching the model to arrive at the correct solution without, again, having to update weights. So you can achieve effective, almost, you can rival performance of fine-tuned models just with appropriate prompt engineering as well. And there's a lot of resources for this. It's become a little bit of a meme. There's people that create these guides to say, you're using ChatGPT wrong. Here's 10 ways to use it correctly. So your mileage may vary here. It's a lot of intuition as opposed to being derived theoretically, although there is a good amount of theoretical work being done in this area as well. Again, we'll be sharing these slides and feel free to click through on these links. We've embedded a number of links that we think might be helpful. And maybe we can just take a few more questions here before we move on. Let's see, average cost to generate M for non-English language. Can we use Amazon, Google Cloud servers? Yeah, that's a good point. Most LLMs are optimized in the English language. Not to say that they're not trained on other languages as well. Usually they are, just considering the internet contains many different languages. So if we're talking about like fine tuning, that really depends on just the size of your trained data set. People have found that you actually need surprisingly little data for the model to perform well on certain tasks. So we're not thinking sort of billions of tokens, maybe more on the scale of even sub-million, so like thousands of tokens or thousands of training examples, may be enough to get it to start performing well on some tasks. And Amazon, Google Cloud, they have pretty sophisticated distributed training platforms for doing this kind of training. So yes, I would absolutely look into using some of those, as well as some of the ones that we mentioned before. Even PyTorch has its own libraries for distributed training. And Eldad, finally, can you share these resources? So we'll send out these slides.
So we also have some on the Q&A, that webinar chat.
Good, lots of questions. Let's see. So Robert asks, can you talk about context window as it relates to building prompts? LLMs use self-attention. So this means that as the size of my context window grows, it's really growing at a quadratic rate. So if I doubled on my context window, there's a quadratic relationship in terms of the size of the memory that I need. So that's the limiting factor. In terms of building prompts, yeah, that is an inherent limitation, how many training examples you can fit into your prompt. Now I believe they scale up to 32,000 for GPT-4, which is considered 32,000 tokens. So you can think about it as maybe a little less than 30,000 words. And there's a lot of research being done in terms of trying to bring down the cost of the context window to, I think in a few years, we will see considerably larger context windows because there's a lot of optimization happening under the hood in terms of low-level implementations of these models. Let's see how we're doing on time. Maybe we can answer a few more questions and we'll save the rest for the end. So Sernjani, can we fine tune using prompt as well? Yeah, we can consider that as a form of fine tuning without updating weights. So yes, I would consider that a form of fine tuning. So Chris asks, trying to wrap my head around fine tuning an OpenAI model that is not available for download. That's right. So they train the model and they save the model on their end. You don't get to download that, but you can query that model. The trade-off is, yeah, you don't get access to your model, which is unfortunate, but you also don't have to incur the cost of training or even storing that model. You would pay basically per token of using that model that you've trained there. Hope that answers your question. When fine-tuning, are you forking an existing model? Yes, so you're taking existing model weights and then you're updating those model weights on your own end. That's right. I think forking is a good way of thinking about that. What about performance methods like LoRa? Is it possible to use multiple LoRas? So we can get into technical details in terms of these parameters later on. Is it better to fine-tune or use information retrieval? I think that question doesn't have a sort of a solid answer yet. I think people are exploring both. I personally really like the idea of using information retrieval. So to give a little context, do we need the model to learn and embed all this information in its weights itself? That seems like it's a little bit inefficient. Rather, can we train a lighter weight LLM to be able to query a database and just find information that's existing, let's say like SQL or even just documents? I think that it would be my take in terms of what is the future of these things, these LLMs, is that, yeah, I think there is a lot of inefficiency in just trying to bake in information in model weights. That tends to be more expensive. So Johnny, with prompting, the weights do not change. Then how does the model learn? Yeah, that's really, people call transformers general purpose computers. It's a really trippy way of thinking about it. The way that the model encodes a prompt is that it learns the relationship between each word or each token to every other token. And in doing so, it's during inference time adjusting weights, right? And so there's some parallels in terms of people talking about transformers as general purpose computers. But in this case, we don't need to update the weights because in the self-attention mechanism, it is generating new weights. And so obviously that learning doesn't survive past one inference. The model doesn't update based on the information you ask it. Every time you give it a new prompt, it's like starting back to zero. But it is, yeah, it speaks to the model architecture of self-attention and transformers that is able to learn in that, just in the context of your prompt.
Great. So these are really good questions. We have just a section here, which is want to just provide what are the broad themes that researchers are thinking about when it comes to LLM. So I'll cover one and Eric will cover the other. And yeah, one thing is there's still an open debate in terms of winner takes all versus open source. And I think this is one of the most interesting things that we've come across is that there is this trade-off and an implicit kind of a deal that us as customers make when we use LLMs. The deal so far is that a company like OpenAI has been able to devote hundreds of millions, if not billion-dollar resources to training and most importantly, figuring out how to make this model palatable to the public. There's a lot of work in figuring out what prompts can or can't not be asked and cleaning the data. And that there's one camp which says that's best done within companies that have a limited number of decision makers who are able to make choices in terms of what is suitable or not suitable. Right? So Sam Altman has high profile, gone around to talk to different regulators, talk to Congress about regulating AI, maybe even saying these are people who can develop and these are people who cannot develop AI. So this is one world right there, right? The other world is a lot of researchers believe that AI in the hands of a few may not be the best and most ethical way to roll this out. For example, those at Meta might believe that it's best to open source the software and have the masses decide what is the best direction for LLMs. So right now, this is why we're stuck in this weird world where sometimes you can fine tune a model, but you don't have access to it. Sometimes you can just take the model itself, do whatever you want with it, and it just sits on your computer. And so we believe that this is something that's going to be really large in terms of its impact on the average person, in terms of which path goes forward and what happens here. Let Eric cover this one.
So just to give a couple of examples of these, obviously this is not comprehensive, but the lab that Kevin and I are working in, we've done some research in this area. One of these risks is as GPT models like ChatGPT becomes more ubiquitous, people will use it to generate text, maybe pass it off as their own, right? Or maybe just use it to improve their writing styles. And with that, there's been tools that have been developed, detectors, to say, is this text coming from GPT or is it written by a human? And they've come out in a flurry. And if any of you have used something like Turnitin before for class, so it scans your text for potential plagiarism. So Turnitin now has a GPT detector as well. So, this one work that I was a part of looked at writing from native speakers versus non-native speakers and found that GPT detector models are actually not very good. In this case, it tends to bias against non-native speakers in the sense that it classifies them as AI generated majority of time, while other native speaking or native English writing samples were not. So that's problematic. And the reason that happens is because most of these detectors really use a proxy for what it considers AI generated. And it basically looks at the diversity of the language generated, right? Because GPT is always looking at maximum probability for each token, it tends to follow a repeatable pattern. And these words tend to be quite predictable, not as diverse in terms of linguistic diversity. And so as a result, it's possible that non-native speakers can be penalized. So this is something that you need to be cautious about. It's a valid question. It's a valid concern. We don't want there to be people passing off GPT writing as human written, but also it can be just as problematic to use detectors, which are not that sophisticated yet, to try to figure out which ones are or not. And here's another work, again, from some friends in our lab. So far, we've talked about LLMs in the context of just like ChatGPT, so text to text, right? LLMs are also used for models like Stable Diffusion, where it's text to image, and actually uses a lot of similar backbone. Here, again, models just reflect the distribution of data that they're trained on, right? So whatever biases there are in the real world, models will learn to reflect that. And that's just the nature of the optimization scheme that we use. So on one hand, it's not surprising, but on the other hand, it's a valid question in terms of if we're using these models, for example, for creative means, right? Or we're using them for teaching means, it is important that we are able to say, first of all, what are the biases that these models continue to reflect? And what are ways in which we can rectify this based on values that we have? And there's a lot of good work being done in this area, not to say that this is an unsolvable problem, but it really has to do with aligning these AI models to reflect the values that we do care about. So here we found that most of these diffusion models really show biases beyond what. So here it shows a couple of models like Midjourney, DALL-E 2, Stable Diffusion. If we ask to produce a photo of face of a surgeon, it produces one type of surgeon, one type of face, for example. Yeah, so these are things just to keep in mind. These are problems that as an industry that people are starting to recognize, starting to come up with ways to solve. Hopefully some of you as well are thinking about these things, can also come up with ways in which we can solve this. Yeah, so something that's good to keep in mind nonetheless.
Okay, great. Yeah, so that's the end of this talk. We'll stay on a few more minutes for any other questions that come along. We just want to remind you that this is the tip of the iceberg in terms of a lot of the technical components. And so if you felt like you're yearning for more specific in terms of like how will you actually take a model, fine tune it, go forward with it. Yeah, feel free to visit our Deep Learning Essentials for those of you who are subscribers to CoRise already. And then secondly, just feel free to connect with us on LinkedIn. I'm happy to chat about any other questions you might have. but just make ourselves available as a resource in general for this community. And yeah, so we'll hop to questions for those of you who attended. Yeah, thanks very much for your time, and I appreciate you joining us. Yeah, Robert asked a question. I'm curious on your thoughts of how the web will evolve based on LLMs. It's a great question. I think this is something that everyone can have an answer to. Within our lab, we've talked about this a few times. There's a couple themes. First of all, is the idea that as the amount of AI generated content increases, the amount of diversity in the content may decrease. And so it might be leading to this sort of feedback loop. But that really depends on a matter of scale and time. So if we look at the scale of content produced in training, that's quite large. And so the question is, how will that affect the actual model itself? The second thing I think was maybe a little more concerning is that it gets really hard to evaluate how well LLMs work. When your training set is the entirety of the internet, how do you evaluate when it's being unbiased or when it generalizes well? You may be drawing from the same source of information as well. As machine learning practitioners, it's something we always are concerned about. Okay, on the webinar chat, Richard asked, I want to do AI research, what are the prerequisites? This is something that evolves constantly. When Eric and I entered research in 2016, we were at a position where people need to know a little bit more math, have a background in coding, and be basically strong in a lot of areas which are traditional in terms of math and statistics. Nowadays, I think just having a lot of ability to code things up and be able to follow trends and so forth are more important. But it depends on the type of research and it depends on the type of lab. So I'm happy to chat more about that offline if you'd like to reach out. But overall, I think it's just the ability to be able to spin up a lot of different projects and be interested in asking questions.
So Peter, I think you had asked a question earlier that I said to get back to in terms of methods like LoRA. So for those not familiar, so LoRA is a way in which you can make a model more sparse. So stands for low rank approximation. I've seen this used in terms of the optimization scheme. So for example, we mentioned Hugging Face, they have the auto train method. One of the parameters you can use is introducing regularization during fine tuning. So there's even just hyperparameters that you can optimize in terms of how to introduce that low rank, that sparsity in your model. So check out that link. Stanley asks, can you use LLMs to generate music of a given instrument? That's really fascinating. I would love to see more work in terms of music generation. LLMs are good at sequence modeling. Certainly music, you can think of as a sequence, right? Because there's patterns, there's regularity there. I think one limitation is that music tends to be very high sampling rate, right? So we think about things like maybe 40 or 60,000 samples per second for sort of high fidelity audio. So you need to have that many tokens in a sense per second. So I think one limitation is computationally, you're gonna have to generate a lot more data. And also second, our ears are very attuned to pick up just slight errors or things that don't sound so well. We're actually surprisingly attuned to that. So as a result, there's been a lot of work in music, but so far I think it's lagged a little behind because compared to like vision, we are forgiving, right? We can blur out things. Things look approximately good. If you see a stable diffusion model of 6 hands, we're like, that's okay. But if you hear something that's even a little bit off, we're a lot more sensitive to that. But I think there's going to be a lot of really interesting research in coming years as regard to music.
Yeah, I would point you also to, so this week, Meta had released something called Music Gen. I believe that's the name. So if you're interested in that, they did something that did a pretty good job in terms of you type in a text and the output music. Yeah, so Chris asked, what early stage startups do you see for software engineers without a background in ML? Yeah, to be honest, I'm not too caught up on early stage startups in general, being in academia. I think maybe one good way to look at it is look at a popular VC like Andreessen Horowitz or Social Ventures or something like that, and just look at their partner company that they invest in and maybe look at their website profiles and see what the qualifications are. Yeah, there's an increasing appetite for people who are broadly interested in AI, may not have an explicit ML background.
Great. Ask the first model you worked with. That's a great question. The very first model was probably like a convolutional neural net. So this was back, I think, in 2015 or 2016. So much smaller models. And actually, people cared about things like exactly the number of layers, number of nodes per layer, what activation functions you're using. Kevin and I both spent hours and untold hours optimizing each of those. Thankfully, now there's a lot more research gone into this where we don't have to worry about these. But yeah, those were good times, nonetheless.
Yeah, Andrew is also a CoRise instructor. He's taught the Stanford course in generating essentially audio and then processing speech. And I think he's a good resource in general. I'd like to check out his offerings. But yeah, he mentioned that there's new work in being able to generate music with musician voices and music scores. But yeah, I just want to pub Andrew in general. He's one of the experts in this field. It'd be great to see what kind of stuff is in this class and so forth. Poen says that there's a lot of focus on fine-tuning the two ends of the spectrum. What about embedding? Yeah, I think that's something that as researchers, we always like to have a principled view on these things and for it to make sense. Like, why don't embeddings really work that well? Part of it is that embeddings right now are still in this world where it's instead of both, it's neither. And so embeddings get you this hard to understand level of abstraction. You might not get exactly what you want. And so it's still something that needs to be developed and matured over time. That's unfortunately kind of the world that we're in. Yeah, and Stanley, if you're not available for the first day, are you able to catch up? Absolutely. I know the first day is actually Juneteenth. It's a little bit of a collision of the first day of our course and the national holiday. We'll make it provisions that you can certainly catch up either that following week or the Wednesday that follows that Monday. Okay. Eric, would you like to take the last two? I think we have.
See, so Chris asks, what roles are there for software engineers that don't necessarily have an ML background, i.e. what is necessary to break into space without a PhD or research background? If you'd asked this question a few years ago, I think the answer would have been somewhat different. I think in a very short amount of time, there's been so much more work available for people that, like Kevin said, don't have a quote unquote traditional ML background. First of all, because models are getting huge, there's, I think, significant demand for people who are familiar with even just DevOps, right? So how do I spin up lots of resources and how do I manage training models or fine-tuning models or even deploying large language models? So that's a huge need. I think there's not a lot of people with expertise there. So if you come from a software engineering background in which you have that experience, I think that's very valuable. In terms of the capability of LLMs, because a lot of what you traditionally think of as starting from a theoretical approach and trying to debug issues with machine learning models, that since they've gotten so large, a lot of the way in which we interface with models is really through prompting now. So even thinking about constructing and reverse engineering what are good sets of prompts, I think that's something that is very valuable for companies. And then also just learning how to integrate APIs that are available or how to leverage these smaller language models. I think these are all very immediate ways in which someone without a traditional ML background can really get into ML. I'm sure there's other things I'm missing, but that's just a little flavor. Shreya, any recommendations for TS models? So this is like text-to-speech models, I guess for dubbing. I don't know any off the top of my head. I know there is models the other way around, so like speech to text, but yeah, I don't know of any tools that I would recommend. Yeah, maybe Andrew, if you have more thoughts there. Okay.
Yeah, there certainly are some like available AI options out there. The other day, I had described to a trial of one that takes voice and try to learn the generative model of your own voice. In terms of open source models, not really sure, but I think some of these companies these days have been able to produce some pretty neat offerings. And so I'll try to include that into the slide after this. I'm blanking on the name of the company that I paid $7.99 to get access to, so I can get back to you on that.
Yeah, if anyone knows any, if they want to post in the chat, that'd be helpful. Thanks. Yeah, thanks, Andrew. Does your course help to get a job to generate LLM and use them for clients' needs to retrieve info from text? To do so is really learning how to leverage APIs. We do cover how to use APIs like from OpenAI. So if that's something you're looking for, is like, how do I generate something from LLM, use it, incorporate it into a programming flow? We do cover that. So we'll have our 4th week module where it's really just very applied. So yes, it will be covering the basics of how do you think about even like design trade-offs there. Great. Any other questions? I think maybe we can take one more since we're a little over time.
And Wes, thanks for posting. 11 Labs was the name of the company that I checked out. So that was it.
Yeah. Again, would love to keep the conversation going. Feel free to add us on LinkedIn, or if you're on Slack, send messages. We really learn a lot from just people in this field as well while we're teaching these classes. So it's a really exciting time, really exciting field. Yeah, thanks for joining us in talking about LLMs.
Thank you.
Yeah, thank you. Yeah, and hope to see you all again soon through the course or otherwise. And yeah, Andrew is on Slack as well.
And if you want to take the course, the seats are still open, so you can feel free to register for Deep Learning Essentials on CoRise, and we'll see you soon.